Hi, everyone. This is a brief introduction to our activities and services provided at Faculty of Engineering, Science and Technology of UiT, the Arctic University of Norway. UiT, the Arctic University of Norway, is the third largest university in the country and the northernmost university of the world. Its location on the edge of the Arctic implies a mission. The Arctic is of interesting and increasing global importance. Climate change, the exploitation of Arctic resource and environmental threats are topics of great public concern, and which the Arctic University of Norway takes special interest in. Our university has approximately 4,000 employees and an annual budget around $400 million US. Around 20% of the funding comes from national, international, and industry research programs. The university has 10 campuses spreading all over the northern part of Norway. Our university has a vision of being driving force in the north, particularly in 5 areas: energy, climate, society, and environment as the first, sustainable use of resources and technology, health and welfare and quality of life, and finally, community development and democratization. Faculty of Engineering, Science and Technology is one of 6 faculties of the university and has 14,000 students and 170 employees in 5 of the university's 10 campuses. The mission of the faculty is threefold. The first is to develop and offer engineering studies that is relevant to the region we are located in. The second is to conduct R&D activities which can strengthen the competitiveness of regional industries. The third mission is to conduct curiosity-driven research for pursuing sustainability and innovation. Our faculty has extensive competence in all engineering fields and is offering 7 bachelor, 6 master, and 1 PhD programs in engineering. The faculty's research is profiled in many of its research units, such as Arctic technology and icing, electromechanical systems, simulation, intelligent manufacturing, and logistics and material science. 3 competence centers are offering further closer cooperation with regional industries such as ArcLoc, BA Center, and ARC Center. We have also 40+ laboratories in all engineering fields. ArcLoc Center aims to be a leading national center for promoting efficient and sustainable logistics operations in the Arctic. The rationale of ArcLoc is that industries in Arctic region are particularly challenged by the harsh climate, vulnerable environments, as well as limited logistics infrastructure. This leads to the needs to connect academia, research institutions closely with industries for the purpose of funding solutions for maximizing the utilization of existing resources through benefiting from the technological advancement in engineering and management. The center contributes also to innovative value generation through competence building and enhancement. So a sustainable development through logistics innovation is the ultimate goal of the ArcLoc. The center has 5 focus industries. They are aquaculture, health, tourism, manufacturing, and transportation. BA Center North is a competence center for construction industry in the region. The center works on topics as digital construction in cold climates, building information modeling, construction in cold climates, simulation and visualization of ground conditions during seasonal variation. For Arctic Center for Sustainable Energy, the interdisciplinary collaboration is crucial. The research in this center is especially conducted in the intersection of social sciences, nature sciences, and technology, which has strong belief to contribute to a green transformation in society. So to summarize, the services we provided are primarily educational program we offer at bachelor, master, and doctoral levels. Also, the faculty offers shorter courses to tailor competence building for facilitating a lifelong learning during different phases of working life. We are also strongly engaged to work closely with relevant industries in the region and Europe for increasing business innovation and sustainability. Therefore, we are constantly seeking opportunities for joint venture. Our 3 competence centers are the first points industry can use to start a contact with us. In fact, most of our previous and ongoing research projects are industry-oriented. To ensure the success of this project, it is common practice for us to engage research teams from different disciplines. Also, as mentioned, the faculty has some 40+ laboratories. These can be provided as workshops and testing centers to industry for technological trial and product prototyping. This presentation will follow by a video which shows some of the laboratory facility we have at the faculty. For more information, please visit us at our webpage. Thank you very much for your attention, and we're looking forward to possible cooperation.
Well, this is our drone lab. Basically here we develop new control laws for the drones and for any mobile robot actually. This is one of the drones that we're still working on. We can see we have our position system. We can say that is our indoor GPS. This is a camera system that is sending some infrared light to these markers. So what the camera sees is only these markers and some reflectors of the light. So when we use this, we can estimate the position, velocity, orientation, or whatever thing that we need inside of the drone. So all of this information is computed by our computer, send the information to the drone, and we can test our control loss. So we have many different types of drone. This is a small one for security in the beginning. This is a bigger one, but they have the protections already. And we can use a bigger one, but well, we need to be sure that our control law is working properly before to test it in a more dangerous drone.
Hello, my name is Haldor. I'm working as a PhD student here for the Arctic University of Norway, but I'm also working in the Trinity project. Today I will be presenting to you the demonstrators we have created here at the university, but also the modules inside these demonstrators we have created. Existing Trinity use case demonstrations. So in Trinity, we are focusing on three main concepts, which is robotics, IoT, and cybersecurity. In the Trinity project, we have created quite a few demonstrations in these three areas, mainly focusing on robotics. And as you can see here, most of the demonstrations that have been created so far are mainly focusing on robotics and IoT again. Demonstrators. So in the Trinity project, as I mentioned, we have created multiple demonstrators. However, these demonstrators usually contain a lot of different technology. Therefore, these demonstrators can again be divided into modules, where one module represents one part of the technology which is in the whole demonstrator or use case. In the Trinity website, you can find all the use cases and modules under the catalog as seen on the right figure here, where you can hopefully get inspiration and find out more information about what technology we have been developing during the Trinity project. So at the Arctic University of Norway, or UiT, we have created two use cases. The first one is called BioArc Additive Manufacturing with Industrial Robots. This use case focuses on using a robot to perform additive manufacturing with a welding robot. And then, in other words, being able to 3D print with a welding robot. Our second module is called Production Flow Simulation / Supervision. This module focuses on digitalization of your current manufacturing or production environment, as well as how to connect your environment together for unified communication between all machines, and also looks at different examples of how you can control and program your system when it has been connected together. BioArc Additive Manufacturing with Industrial Robots. So our first demonstrator, again called BioArc Additive Manufacturing with Industrial Robots, it can be divided again into two modules. Well, the first module is called Simulation Welding. This module focuses on looking at how to use a simulation software to program a welding robot. The second module is called Additive TIG Welding. In this case, using the same setup from the first module, however, expanding it and being able to do additive manufacturing or 3D printing with the same system. This again can be used to create parts or repair broken parts. So for our first module, we are using a program called Visual Components. This is a rather simple software which allows us to create a digital twin of our current welding cell, as you can see on the picture. And it also has a simple interface for programming of a robot program. In this case here, we are running a program on the digital copy, so doing offline simulation to check if everything is okay, welding a half a circle. Then afterwards, when we have created the system, we can take the same system or program and execute it directly on the physical system. This again allows for offline programming, and you can test your program in an offline simulation before running it on the physical system, as it can be quite dangerous running such a program on the real robot itself. Our second module, it uses the same program and same setup as before, however this time doing additive manufacturing or 3D printing. So in this case, we program a simple path. Then afterwards, our program will automatically generate multiple layers with a fixed increment between each round. And here, after we have run the simulation offline, then we can actually execute the same program on the physical robot. And here we are just 3D printing a small line, putting layer per layer. And again, this system can be used to repair parts, but it can also be a rapid method to create small structures. So this can be an alternative to, say, using a CNC 5-axis machine, rather to use industrial robots. Then less material is often used when doing 3D printing compared to material removal. Our second demonstrator is called Production Flow Simulation / Supervision. So this demonstrator can be divided into 4 modules. The first module is called Rapid Mapping of a Production System in a Virtual Environment. So this module looks at how to rapidly create a digital twin of your physical production or manufacturing system. The second module is called Connecting Virtual Model with the Physical Model. This module looks at how to connect your physical system with your digital system and enable communication also between machines for machine-to-machine communication. The third module is called Remote Control for Industrial Robots. This module looks at how you can remotely control and program your industrial robot with a simple interface. And the fourth module is called Virtual Reality Programming of a Manufacturing Cell. This module looks at how you can use VR for programming of robots, but also for your whole system. So the first module, rapid mapping of a production system in a virtual environment. So in our case, we actually use a mobile robot to map our production environment or our laboratory in our case by just driving around a mobile robot, mapping all the walls and objects in the environment. From this scan, we then get a 2D map, which we can then import into, in this case, it's visual component, put in all the walls, all the robots, tables, and so on, scale it to the right size, and so on. And then afterwards, we have a digital copy of our production or our laboratory, which we can then again use for simulation, testing, and also optimization of our production in the environment or laboratory. Having a digital copy of your physical systems allows for a lot of flexibility. You can also see if machines and robots will actually fit inside the environment. The second module is called Connecting Virtual Model with the Physical Model. So this module, in very simple terms, looks at how you can connect together robots and machines using a unified communication method. In our case, we're going to show how to use the OPC UA standard for machine-to-machine communication, and it also allows you to directly connect your physical environment with your digital environment. And this is, again, very important to enable communication between all parts of your system. The third module is called Remote Control for Industrial Robots. So this module, it looks at how you can remotely control your robot with one user interface. So this means that you can use the same user interface to control multiple robots, and you don't have to jump between different robot controllers. Say if you have different brands on the robots, you can still use the same user interface to control the robots. And again, this user interface is also remote, which creates a lot of flexibility. And as long as you are connected to the network, you can use any device that has a network browser to then again control your robots. This again creates a unified method for robot control of your robots again. So our fourth and last module is called Virtual Reality Programming of a Manufacturing Cell. So this module, it looks at how you can use virtual reality for programming of both robots, but also the whole system itself. So here I'm going to show you some examples where I am in the lab and programming this Nachi robot. So first here I'm adding positions to the robot arm, then afterwards executing the program in virtual reality to see if it is acceptable. Then afterwards pressing the black button, which allows me to directly transfer the same program over to the physical robot. I can then execute the same program on the physical robot, and it is also one-to-one compared to the robot. We also have can use the same interface to also program, say, for example, the SCAR robot. In this example, to pick up a cube, afterwards move the cube to the side, and then move away from the cube. So it goes down, picks up the cube, and then it leaves it and goes to the middle. And this program, again, can be directly transferred to the physical system and executed on the robot. And here again, we're using the same connectivity functions as we created in the second module. We can also use this same or a similar method to control our mobile robot. So we walk around the laboratory, pressing the A button on the controller, which creates a yellow marker. The mobile robot will then drive to this marker, which is then a position it will drive to. Afterwards, we can actually execute this program to see how where the mobile robot will drive. And again, afterwards, when we have tested it here in the simulation software, we can then directly execute this program on actually the physical machine or mobile robot. So here you can see the mobile robot. Up in the corner, you have the map for the mobile robots. And as it drives to one position, it gets a new position order and drives to it. And we have created the digital model and physical model to be one-to-one. And for last, we have here an example where we are programming all of our robots, which we have in our lab with VR. And creating here, this is a demonstration where the mobile robot, it will drive to a robot arm. The robot arm will then do a small movement. And when the robot arm has done the small movement, the mobile robot will then continue to the next robot arm. And in this example, we have also included our KUKA robot, as you can see here. And again, as I mentioned previously, when all the positions have been added, we can then actually execute the same program we created, see how it will move in the virtual world before then executing it afterwards in the physical world. And here is the physical world where we are executing the same program as we had created previously. I can also mention having the ability to program system in VR. It creates a safe and reliable method for robot programming compared to doing it on the physical system. Having the ability to do it in the virtual environment creates a lot of safety. Thank you. These are our use case demonstrations we have created here at the Arctic University of Norway. If you want more information on them, please check out our Trinity website for more information, and also look at other Trinity demonstrations that have been created by our other partners. Thank you. I will now present work we have recently been doing here at the university, where we have been developing a flexible, autonomous industrial mobile manipulator for improved agility and efficiency in manufacturing. The problem statement for this project. So the world is today going from mass production to more personalized and customized production, or mass personalized customization. However, going from mass production and mass personalized customization requires you to have a more flexible and agile manufacturing system. And your manufacturing system will also be able to change more rapidly and be more flexible. So AI/MM, they are usually made to work besides people, not interfere. And as you can see, they are built to be modular, where they can automatically drive around a production or manufacturing environment. And they can perform tasks at different workstations, say going from a CNC machine and then afterwards working with turning machines, feeding in parts automatically. And there's one thing which you can note by the AIM, it is built up by using different concepts from Industry 4.0. For instance, on the top, you have robot arm. On the bottom, you have a mobile robot, which can autonomously drive around without guidance. You also rely heavily on IoT connectivity. And again, also, of course, cybersecurity and so on. So these AI/MM, they are a merger of different Industry 4.0 concepts. From our side, we had a new idea for the AIM. So normally an AIM, it is built with a mobile robot in the base and a collaborative robot on top. sometimes just normal industrial robots on the top. It depends on the use case. So our new concept, or our new idea, is to then divide up these two parts. And the reason for this is, since when the mobile robot is driving, the robot arm is usually not working. And while the robot arm is working, say picking up objects or sorting, the mobile robot, it stands still. Therefore, you get limited utilization of both the mobile robot and robot arm. Therefore, we want to divide these two into two parts to increase the utilization of both parts. Again, I will also mention that mobile robot and robot arm, they are both extremely expensive investments. And it is therefore, again, important to get the most utilization of both parts. We have a mobile robot in the lab. As you can see on the picture here, it's a Mir 100. And on top of it, we have created a hooking system where there are two pins that move out to the side to be able to fasten itself to a trolley. And then we have two robot arms, a SCAR robot in the middle, fastened on a trolley with a battery and the robot controller. And on the right-hand side, you have the Nachi robot 6-axis robot arm placed on the trolley again with a battery pack and also the robot controller. So both of these robot arms can work autonomously without power or any connection, and there is a control unit. Our mobile robot is then able to pick up both the SCAR robot and the Nachi robot. So we only need one mobile robot to service two robot arms. Connection. So usually when you have an AI-MM, you usually need communication between all parts to be able to send missions and tasks to both the mobile robot and the trolley with the robot arm. In our case, we ended up using the OPC UA standard for connectivity between all of these parts. In our case, the OPC UA standard, it gives us machine-to-machine communication and also machine-to-machine communication between robots from different brands. As you can see, we have a SCARA Adapt robot on one trolley, and then we have a Nachi robot on the second trolley, and we also have the Mir. So for the picking system, we 3D printed a gripper and fastened an electromagnet at the bottom of it, as you can see from the figure. And we also attached 3D cameras to be able to detect objects automatically, but also to see the depth and how far away the objects are. And here is a simple demonstration where we are running the pickup system. So the system works where the robot arms arrive at a station. They will then move out. They will then drive a routine to check if they can find a screw. If they find a screw, then they will position themselves for the screw, and then afterwards automatically move down and pick up the screw. And this system has been run multiple times where the robot's arms are able to pick up the screw at different positions and being able to differentiate between different objects. The reason we need this pickup system is since the mobile robot moves around the trolleys won't be in an accurate position to be able to run pre-programmed programs. Therefore, it is better to use image recognition and artificial intelligence. So control architecture. So for this system, as I mentioned before, all the robots, they are, and all the machines also have been connected to the same OPC UA server, which allows for unified machine-to-machine communication. So on the top here on the figure, you have a control computer. This is the human operator. The human operator sends out a mission to either the Nachi robot or a SCAR trolley. For instance, drive to the compact lift or vertical storage and pick up a screw. Then afterwards, the Nachi robot, it will control and ask the mobile robot to come and pick it up and drive it to the compact lift. When it then arrives at the compact lift, the Nachi robot will then ask it for, say, drawer number 18, and the compact lift will automatically get this drawer. So this is a hierarchy of control for such a system. But again, this system is heavily on a lot of optimization for the Nachi trolley and SCAR trolley for this system again to work. And here is a demonstration video. We have the mobile robot map on the right-hand bottom. In this case, the mobile robot has been, or the Nachi robot has asked the mobile robot to come and pick it up from this station, and then afterwards transport it to the compact lift. And as you can see in the front here, there is a marker which the mobile robot is using to dock to get a little bit more accuracy when positioning. Then afterwards now, the Nachi robot, asks for a drawer and will then afterwards now start looking for a screw and try to pick up a screw from the compact lift. Then our SCAR robot will then ask to be transported to the same location that the Nachi robot was just at. And again, the kind of idea of this demonstration is to showcase how one mobile robot can be used to serve not only 2 robot arms, but also a platform now afterwards. Again, this SCAR robot will then start picking up screws. I'll also mention that in this case, we have been focusing on AI or AIMM, transporting robots. However, we can also do logistics tasks, such as just transporting around goods in a factory or a manufacturing system. So this is just showcasing that it can serve different. Again, we get here more utilization of the mobile robot and also both robot arms, which are again very expensive investments. So conclusion, the AIMM, it's a very flexible solution for a manufacturing system. However, dividing the system in 2 with a mobile robot at the bottom and the robot arm at the top, splitting them, having a trolley with a robot arm and a mobile robot, it can allow you to get more utilization of both the mobile robot and robot arms, instead of having one of them always standing idle while the other one is working. And I will also mention that from our experience, using the OPC UA standard for communication is an excellent solution to get communication between all machines. And also could also see we were able to get communication with the compact lift and all both the robot arms and the mobile robot seamlessly without any problems. Thank you for watching this video.